Hello, this is Dr. Baxley. This is part 2 of the Chapter 4 lecture video series. This video is all about molarity, with a little bit at the end about mental models and how to draw pictures of what's happening in solution. This chapter starts off with solution concentration units, especially molarity. Molarity is a really useful ratio of the number of moles of a solute per volume in liters. So the ratio works out like this. It's the number of moles per 1 liter, and molarity is often given the symbol capital M. However, I urge students to always translate capital M into moles per liter. Remember the old trick about using numerator-denominator fractions? It's really important in this case for molarity. Molarity can be used like a conversion factor. One can take the volume of a solution and multiply it by the molarity in terms of number of moles per liter. If you multiply volume times moles per liter, you end up with the quantity of the number of moles. If you take the number of moles that may be needed for a particular reaction, and you multiply it by the inverse of the molarity, for example, 1 liter for a certain number of moles, you'll calculate the volume that contains that number of moles. Ready for some examples? First of all, we're going to look at how many moles of sodium fluoride are present in 150 milliliters of 0.200 molar solution. First, the units of milliliters need to be converted to liters, but I'm sure you're almost an expert at that at this point. Here's the 150.0 milliliters. That would get multiplied by 1 milliliter for every 0.001 liters. That works out to be 0.150 liters. The volume in liters can then be multiplied by the molarity, just like the equation we looked at on the previous slide, to calculate number of moles. 0.150 liters multiplied by 0.200. I'm going to convert or switch the capital M to moles per liter. And the result is 0.0300 moles of sodium fluoride in that solution. Using the same concentration of solution, the 0.2 molar NaF, this question asks what volume of that solution would contain a certain number of moles of NaF. Starting with the measured value, it's not a ratio, 0.0420 moles of NaF. Remember, the molarity, the capital M, is just that ratio of moles per liter. That can be used in the inverse. So for every 0.200 moles, there would be 1 liter of solution. This would work out to be 0.210 liters of solution would have 0.0420 moles. Last sample question, what volume of 1.500 molar solution has 22 grams of calcium fluoride? We're being asked about a volume of a solution, and we know the molarity. Well, if we know the number of moles of the solute we're trying to have to get that certain mass, we might be able to use the molarity as a ratio between volume and moles. We can start with a 22.00 grams of calcium fluoride, CaF2. If we multiply it by the molar mass, We could then calculate the number of moles of calcium fluoride. That works out to be 0.2818 moles of the calcium fluoride. Once the number of moles is known, that can then be multiplied by the molarity in some fashion. If that value is multiplied by the inverse of the molarity, for every 1 liter, there are 1.500 moles. That would work out to be 0.1878 liters of solution would have the 22 grams of calcium fluoride. We can use this information about molarity to learn how to make solutions and determine concentrations of those solutions. So here's a little diagram. A chemist takes solid sodium chloride and measures out 58.44 grams of it and adds it to a container. This container is called a volumetric flask. It holds a specific volume of liquid at 1 etch mark. The chemist then dissolves the substance in water and adds water all the way up to the 2.00 liter mark. So the total volume of the solution is now 2 liters. We can now calculate the molarity of the solution. In order to calculate molarity, you need to know 2 things. You need to know moles, and you need to know volume in liters. Oftentimes when students ask me a question, "Hey, Dr. Baxley, how do I calculate the molarity of this substance?" In this particular problem, I'll ask the student a question. I'll say, "What 2 things do you need to know to calculate molarity?" And the student will say, "Oh, you need moles and you need the volume." And I'll say, "Of course." And once the student knows those 2 things, that they need moles and volume, oftentimes the problem just flows by itself. So in this particular case, we start off with 58.44 grams of sodium chloride. Conveniently, the molar mass of sodium chloride is 58.44 grams. In order to calculate molarity then, the number of moles has to get divided by the volume. We can show that just as multiplying by 1 over the 2.000 liters. And that works out to be 0.5000 moles per liter. Or we could say that it's 0.5000 molar. Here's another question about making a solution and calculating molarity. In this case, the chemist is trying to calculate the mass of a compound, potassium sulfate, needed to make a certain volume and concentration of a solution. It's a pretty common problem in chemistry labs. One needs to know the formula for the substance being dissolved. Aren't you glad you spent so much time learning how to write formulas and name compounds? Potassium sulfate is K2SO4. In order to solve this problem, we need to know the mass in grams of the potassium sulfate. If we know the volume and the molarity of the solution, we can use volume times molarity to calculate moles. I'm just going to convert the 235 milliliters to liters without showing that step. You should be good enough to be able to do that, or at least see me do it without being concerned. This would be 0.235 liters. That can be multiplied by the 0.152 mole per liter of solution. Once the number of moles of potassium sulfate is known, it can just be multiplied by the molar mass. And that would be 6.22 grams of potassium sulfate that would be needed. Sometimes chemists make solutions from other solutions rather than just solids. In this case, the chemist takes 150 milliliters of a stock solution. This just means it's concentrated. That solution happens to be 6 molar. The chemist takes some of that solution, the 150 milliliters, adds it to a volumetric flask, and then adds water to fill up the flask to a 2.000 liter mark. The question is, what's the concentration of the new solution? You're being asked, what is the concentration? That should be a trigger for you at this point. In order to calculate concentration, you need two different values. Value 1 would be moles, and value number 2 would be volume in liters. Since we know the volume and concentration of the original solution, the number of moles can be calculated. 0.150 liters times the 6.00 moles per 1 liter. At this point, we know the number of moles of the original substance in a small volumetric flask. In the large volumetric flask, it would be the same number of particles. In order to calculate molarity, you would divide that number of moles by the new volume, which is 2.000 liters, yielding a new molarity of 0.450 moles for every 1 liter, or 0.450 molar. Here's another problem about dilution. In this particular case, you're being asked to calculate the volume of a concentrated solution, 6 moles per liter, that's needed to make a larger volume of a more dilute solution. Pause the video and see if you can tackle this problem on your own. Then come back and I'll show you the solution. To solve this particular problem, we can look at what we're given. We're given information about volume and concentration of a solution. This might be a trigger for you now, that if you know volume and concentration in terms of moles per liter, that you might be able to do something with that information. To solve this problem, we'll need to calculate the number of moles in the dilute solution. We need that number of moles to come from the concentrated solution. We can then use the molarity of the concentrated solution to calculate the volume. Let's start with the 0.2500 liters of the dilute solution, multiply it by 0.475 moles per liter. Once the number of moles is known of the number of particles we need from the concentrated solution, that number can be multiplied by, for every 1 liter, 6.00 moles of that substance. And in that case, this works out to be 0.0198 liters of solution. Since this question asked about milliliters, converting that to milliliters would be 19.8 milliliters of solution. If you were reading the text, you'll see this particular formula, M1V1 equals M2V2. And this is a great little formula, but it's exactly what we did in the above problem, and I'll show you how that works. In this particular formula, on each side of the equation is M times V, or molarity times volume. You might already know that molarity in moles per liter times volume in liters will always calculate a number of moles. In a dilution problem, the number of particles coming from one container is always going to be the same as the number of moles in the next container. So what this formula really tells you is that moles of a particle in one container is going to be equal to the moles of that particle in a second container. It's really important that you only use this particular formula for dilution problems. Never use it for a chemical calculation problem. So how is this math the same as what we did before? What we did before was we took volume and concentration for one solution. And then that was divided by the concentration of a second solution. And that worked out to be the volume of the second solution. If we look at this M1V1 equals M2V2 formula algebraically, you can see that if we know M1 and V1, the dilute solution, and we know M2, the concentrated solution, if we solve for V2, it would be equal to M1 V1 over M2, which is exactly what we did above. We multiplied V1 times M1 and then divided by M2 to equal V2. It's really important that students keep the M1 and the V1 together and not get them confused with M1 with V2 or V1 with M2. So make sure you keep those straight. Make sure you never use this formula for chemical reactions where one substance is reacting with another. In that case, you've got to use good old stoichiometry in order to figure out answers. Never use M1V1 equals M2V2 for a problem like this one coming up. Before we get there, we've got the mole highway picture again. Before, we got on the mole highway by using mass and grams per mole. It's also possible to get on the mole highway with volume and the molarity. If you multiply mass times grams per mole, you can get moles out of that. And with volume and molarity, you can get moles. So in either case, you're calculating moles from one of those two things. You can also get off the mole highway with volume and molarity. It works in both ways. Here's a scenario that involves concentrations and volumes and stoichiometry. In this particular case, some lead 2 nitrate is being mixed with potassium iodide. You can see the results of what happens here. On the right, there's a picture of the two reactants. They are clear and colorless in the test tubes. When they're mixed together, you get a beautiful yellow precipitate. So at this point in the class, you know exactly what we should do first before we do anything else. And of course, the first thing you do whenever you have a chemical problem is to write a balanced chemical equation. In order to balance this chemical equation, we can see that there are 2 nitrates in the reactants. There need to be 2 nitrates in the products. Since there are now 2 potassium ions in the products, there need to be 2 in the reactants, and that takes care of the iodide too. Now, based on the solubility rules that you're going to learn about soon, you could predict that the lead 2 iodide was the solid, and the potassium nitrate is the remaining stuff in the aqueous solution. So, how do we get involved in this problem? If this was a problem from the beginning of chapter 4, you would want to know the mass of each reactant and the molar mass. I apologize for the pen, it's getting a little crazy. I think the screen's too hot. I hope I can work around that crazy line. Since we don't have mass and molar mass, but we do have volume and concentration, that ought to give you a trigger as to what we might do to determine number of moles. Of course, volume and concentration, if multiplied together, will yield the number of moles. We can start with the potassium iodide, 0.0250 liters times 0.230 moles of Ki for every 1 liter. Once the number of moles of Ki is known, the mole-to-mole ratios from the balanced chemical equation can be used. And once the number of moles of lead 2 iodide is known, that can be multiplied by the molar mass of lead 2 iodide. And that works out to be 1.33 grams of PbI2. That's possible from the potassium iodide. For the second reactant, the same volume is used, 0.0250 liters. The concentration is a little bit different. It's 0.140 moles for every 1 liter of the lead 2 nitrate. Once the number of moles is known, the mole-to-mole ratio can be used. And once the number of moles of product is known, that can be multiplied by the molar mass. And that would provide 1.61 grams of PbI2. And of course, since you've already done the limiting reactant section, you know that the 1.33 grams of lead 2 iodide is the most that can be made. We're going to totally switch gears here and talk about something else, something you'll need to know for some of the labs that we do. Mental models is a term that chemists use to describe pictures that show how atoms and molecules interact. It's one thing to be able to do some calculations. It's another thing to be able to show that on paper, to describe exactly how things are working in a chemical reaction. In the drawings you do, you're going to use either elemental symbols or shapes and colors to represent the atoms and ions and molecules, or parts of molecules. Here's an example from the textbook. Here's a pretty picture of magnesium burning in oxygen to make magnesium oxide. To show the magnesium, those are just spheres or circles with the little symbol for magnesium metal inside. Notice that magnesium metal has 0 charge. Magnesium, when it forms compounds, is always 2+, but elements in their normal elemental state always have no charge. Just like the oxygen here the magnesium combines with, the O2 also has 0 charge as a molecule, even though oxide as an ion has a 2- charge. So we've got the magnesium, we've got the oxygen, of course it's diatomic, which is shown with the 2 spheres stuck together. Those react together to form magnesium oxide, or having the formula MgO as a solid. And we can see now that this is an ionic compound, so the magnesium is Mg2+, and it's surrounded by oxygens of O2-. So there's a mental model, pretty simple one. It's a nice picture from your book. Here's one we can draw for an aqueous reaction. This one has calcium chloride reacting with sodium sulfate to make a solution of sodium chloride and a calcium sulfate precipitate. Precipitate is just a fancy chemistry word for solid. One important note is that this particular reaction scenario describes there to be an excess of sodium sulfate. Here's a chemical equation. We should check to see if it's balanced. There's calcium chloride reacting with the sodium sulfate to make sodium chloride and calcium sulfate. You can see that there are 2 chlorides in the reactants. There would need to be 2 chlorides in the products. That takes care of the sodium, and the sulfates are balanced already. So we can draw what this might look like. I'm going to draw one container for the calcium chloride solution. Now in aqueous solution, ionic compounds always separate into their component ions. So here's Ca2+, and here's chloride. The Cl sub 2 simply means there are 2 chloride ions for every 1 calcium. I'm going to put another one in here too, calcium 2+, and 2 more chlorides. I'm going to draw another container with the sodium sulfate. And in this particular solution, there'd be 2 sodium ions for every 1 sulfate. I'm going to draw 3 of these total. Now these 2 solutions are going to be mixed together, and I'm going to pour them into a much larger beaker, just so I've got plenty of space to draw all the ions present. We already know that the calcium sulfate is a solid, so looking at the number of calcium ions that are present, 1, 2, and the number of sulfate ions that are present, 1, 2, there can be a total of 2 calcium sulfate blobs as a solid that are prepared in this reaction. A solid would typically be at the bottom of the beaker, so I'm going to show that as kind of a lumpy solid here at the bottom of this container. And that takes care of all the calcium ions in the original solution, plus 2 of the sulfates. Now the other ions aren't doing much. We know there are 4 chloride ions that haven't reacted. We can see there are 6 sodium ions that haven't reacted. And is there anything else that hasn't reacted? Of course, there's 1 more sulfate here that hasn't been dealt with, and so it's got to be in solution too. I should have put the little arrow in for the reaction. So there's a little mental model just showing the symbols of all the elements. It shows the proper ratio of each of the ions in the compound. It shows the proper ratio of the chemical reaction in that 1-to-1 ratio for calcium and sulfate. It shows the products in the right states. Either solid or aqueous. And it shows all of the ions from the beginning to end. I think Dalton would approve. Dalton had the law of conservation of mass and the idea or atomic theory that atoms and ions just rearrange to form new substances. And that's all that's happening here. We have some atoms rearranging, but nothing's being created or destroyed. That's the end of part 2 of chapter 4. There's going to be at least part 3, maybe part 4. I hope you enjoyed. Let me know if you have any feedback.